So actually this is a component, and usually what we do is if we have data, then we get loads of variables. So not only the 2 or the 3 metabolites like we had just a while ago, just in the example before, but we have more than that. So first of all, I will show something like a small introduction, like how we explore the data. Then we go to principal components, the scores and loadings of it, some centering and scaling aspects, combining data sets. I guess that's a nice way, but it's relatively new. It's very popular, very hot item at the moment, but it's not completely clear what we can do with it. Hands-on won't be today, so it's an early evening. So, well, and then, but it will be tomorrow morning. So, and Patricia will do that. So, so if we start to explore the data, what's what we first do? Well, usually we visualize the data. If we have 2 metabolites, for example, x1 and x2, in an experiment in time, we can plot the response against each other, and it seems like this, and it's nice. Wow. And we regress, or we can regress. We can do whatever we want with it, but it seems very trivial, and we can look like, hey, is there a relation? Like, what would be a line there? But usually it's not x1 that drives x2, but it would be, for example, an increased effect of time that causes them both to become larger, and they are correlated. And because they are correlated, I get this plot. For example, if I would draw this line, it could represent growth or something like that. And these time points, t0, these points would be points in time. So what we could do is find some common direction, and in this case it would be the red line. So, and if we would like to summarize our data, we could use only one variable and give it a meaningful name, and of course in our case it could be growth. So what I actually would do is reduce my data and call it growth. There we go. So the new variable actually is the main variable, and it has captured most of the variance. And actually we could consider that a principal component. And it would have weights, in this case normalized. So this times x1 plus that times x2. The coefficients, the weights, describe the way each variable contributes or loads to the growth variable. And we can consider or can refer to the values of growth as scores of growth. And actually growth has become a linear combination of the variables x1 and x2. So, but what if more variables are concerned? So visualization of 2 variables is easy, but even 3 variables can readily be visualized. But already you find that if you want to print them, it's getting hard. So if you want to plot them on paper. So, but if more variables are involved, how would you do that? How could you make a meaningful visualization? And well, for that we have to combine the variables in some smart way. Then just one step back. First of all, my information often comes in the form of matrix, like the metabolites examples or the previous ones I've shown. We got the variables in columns and my objects or samples in the rows. That's, at least for me, a common way to produce it or reproduce it, represent it. For mRNA or sequencing data, it's usually the other way around. I prefer this way, to be honest. So I will, the whole presentation will be like this. So objects in the rows and variables in the columns. And for example, we got spectroscopy, which would be sample times wavelength. Proteomics would be patient times protein or whatever. And metabolomics, like we've seen before, is the subject times a metabolite concentration. Could possibly be. Then what would principal component, what does it entail? Well, first of all, it's a data reduction method. So what does it do? It reduces the large data matrices into 2 smaller matrices, which can be more easily examined, plotted and interpreted. and I will come to that later. What does the PCA allow me to do? Well, first of all, it also allows me to explore my data, because it extracts the most important factors, like we saw earlier, the growth, in principal components from the data, and they describe multivariate interaction between the measured variables in terms of linear equations, linear relations, and it would give me some data understanding, like I can use them to classify samples or identify compound spectra and determine biomarkers and stuff like that. So here I've shown a nice, here I have two plots of sequencing data of the STATegra data set, and actually I've plotted for the whole data set, which is 12,762 genes. I plotted my scores, and actually what is nice to see is that I've got in the PC1 direction, I find a difference in control and study samples, and if I look, even though it's not a clear line from top to bottom, because I've got some trend like this, but I see some discrimination between the time points of my Icarus samples. So that gives me a nice idea, like how they differ and how differ from each other, and well, how reproducible they were measured. And if I look at my microRNA score plot, it almost looks similar, except for the fact that I've got a control versus study on the PC1 direction, but there's no clear time effect here visible in the Icarus samples. If I look at, well, there's no way getting around this. I mean, this is the core of PCA in terms of loadings and scores. And actually what we do is that the basic equation for PCA, we can write that as my X matrix, that's my whole data set, is my first score matrix times my score loadings, or my loading matrix, plus the second one, and and so on, plus an error term. And if I look at, and this is the abbreviation of it, so my scores times my loadings, actually these are factors to be honest, and this is the matrix plus an error term, where X is my data matrix, T the scores, the loadings, so they're concatenated, and E are the residuals, and R is the number of principal components that I've selected. So what are these principal components? They are defined by one pair of loadings and one pair and scores, actually, T, R, P, R, and sometimes they're called latent variables. So what do? They describe the maximum variance, well, like my example, like the growth variable, and they are calculated in order of importance. So my first component is always the one with the most explained variance. The second one has then the most, the third one is then. So it's in decreasing order. And all of them, so if for example I have got maximum 10 components, then then it will add up to 100%. So by using all my components, I have explained all my data, all the variance in my data. So I've got my original data back, but in a different, in components in this case, not in my real, not in the original space. And now, well, this is another way of explaining these layered forms of variance, explains variation. You can see is that the unexplained fraction actually is 100. Well, to make it percentages, 1 minus the error terms, so divided by my original variance. And of course this error term becomes larger if I decide to include fewer components, because then, for example, if I only would include one variable, then this all would go into my error term. So graphically this would mean like I've got scores here, loadings, so X actually, well, X is decomposed in scores and loadings. This is my first component, plus another component, plus a third component, and so on and so on. And in matrix form, we combine them, we concatenate them, and they look like this. And an error term. So, to summarize, my scores and loadings, so what do? The scores, they actually have the relationships between the objects. They are orthogonal, and that's something I will come back to later on. The loadings, they describe the relationships between the variables. They are orthonormal, and actually this is usually used in chemometrics. These demands or constraints, they're really specific to chemometrics. In psychometrics, they can be a bit different. So, but this is the one that we use right now. And similarities and differences between objects or variables can be seen by plotting scores or loadings against each other. The scores are the product of the real values and the loadings, and I will come to that here in the next example, or in the next one of the next slides. And my estimates back are the scores times my loadings. If I go to some example data, again it's an easy one. I've got here some two variables which I've mean centered. And actually what I did is to show you that how the way variance is calculated or captured by the component. First of all, I draw the first component, which is PC1. And these are my coefficients here. And then PC2 I've plotted, which is orthogonal actually to PC1 in this case. So my scores are my original data times my loadings. So, and if I do that, so this is my scores values, then what I see is a sums of squares of 88.9 and 1.1, and in total it's still the 90. So actually what I did is I rotated my data into a new axis environment, where the first component almost explained all of the variation. So, and only the second one is very small, so it's almost of no importance at all. So I actually reduced my data in a very nice way. So, and this actually is one way. Well, this of course is what we can do with PCA. We can reduce our data to a smaller set of principal components, which we can try to explain later on. So in the end, in this example, what would we end up with? Well, first of all, the score plot itself. So I've plotted PC1 against PC2. Now, because PC1 captures almost all of the variance, PC2 is almost importance. So, but we see an increasing time from left to right. So what we expected. And if I look at the loading plot, of course, it's only two variables, so it's not impressive. So, but I see here the value. So the one x1. Oh, actually, these are inverted. Sorry, well, that's my mistake. But actually, if we look at the data, and we should remember that we are often interested in the difference between the objects and not in their absolute values. And this is also a very important part, the centering and scaling. And if different variables are measured in different units, some scaling is needed to give each variable an equal chance of contributing to the model. And this is important if you want to do PCA analysis. So there's a couple of ways. Mean centering is a very commonly used method. And actually what we do is we determine the average of every column and we subtract it, and then, well, we end up with such a data matrix that we can work on, and every average here is 0. Then we can also do some scaling, and then we divide the data by its standard deviation. So every variable will have the same standard deviation, and that's sigma. Standard deviation sigma 1. So we can really compare these variables to each other because they are in the same order of magnitude. So what is the effect then if I just do mean centering? So, and this is some data I've simulated, but just to see the effect. I've generated a couple of variables that have a large variation and variance for that matter. And what you see is if I do a randomly PCA plot, what you will see is that the ones with the high variance, with the large variance, that they dominate the loading plot. So they would, well, you would think that they would have the largest effect. So, and even if they don't have that. So you always have to take care of that you use the proper scaling method. And in the same data set, but actually I did the auto scaling here, you see that, well, I also plotted the standard deviation. Well, there's a whole bar because it's exactly the same value. Everything is scaled to 1. But what you can also see is that everything is in the same order of magnitude and they are within the same range. There's no real dominating loading anymore. And the explained variance, consequently, is also lower than without scaling, because less variation is explained, because these variables, they explain most of the variation in the first place. Then there's another issue, which is how many PCs or principal components to use if we want to do a PCA. That's, well, you can use variance plots, so Scoreplots you can call them. You can see how much every component, how much variation every component explains, and then it becomes tricky because there's almost no clear rule how many you would select. I mean, it's really, in this case I would select 3 because this drop is one of the highest, and then you can go down. There's a couple of other things. You can select the number of components where explained variance is larger than the noise level, but then again, what is the noise level? You have to determine that. You can also look at the PC scores and loadings, and do they still make any sense? So that's really looking at your data. Do the residuals have any structure? And you can do some cross-validation methods. So in conclusion, the principal components analysis, they reduce large collinear matrices into smaller matrices, scores and loadings, like this. And they describe the important variation in the data. And they are calculated in order of importance, and they are orthogonal. So this would be one axis, but this one would be really orthogonal to that. So actually, this would have nothing to do with this one. So it's like an x is perpendicular to y, and that's the whole. I'm working in axis environment. Now, and this is something we're going to use if we want to combine multiple data sets. So this whole idea, it's if we want to fuse data sets. So why would we want to fuse data sets? Well, first of all, like if I have an mRNA or microRNA data set, I want to combine these data sets, and I want to, well, can I relate them to each other, or can I get some more information out of it if I combine them? Because in here, it's not in this presentation, but so, for example, what would be common in this case? Well, for example, if I look at I could have some underlying biological processes on multiple levels. So some biological things could go on in the one data set or in the other one, and I can combine. If I combine the data sets, would I perhaps get this common information out of it? Actually, that's what I'm after. That's what I would really like. So, then again, if there's some systematic deviation for some samples, it could be identified and removed this way. And what I can do is, if I want to look at individual blocks, I can remove my common variation, because individual or distinctive information can also be very important. So, like for example, differences from a common time from a common profile, time profile, could be important. Like, okay, my mRNA works like this, and my microRNA also goes along for a long time. Time point, well, 6, it behaves completely different. I've got some additional information there. and I would really want to identify that. So that's really interesting. And again, conversely, variation that can mask common variation again can be. But that's the interplay between the both of them. So you can, yeah, that's the common and distinctive here. And if, for example, I would look at my two score plots, and in this case these are data sets from the glioblastoma data set, so these are brain tumors. 5 types of brain tumors here, and different colors mean different. And if I look at both of them, I can see, well, do they look similar actually? I mean, what would be the best way to say something about both of them? I mean, compared to each other. I mean, they are exactly the same objects, but my scores are completely different or are different. So can I say something? How can I relate them to, well, so the best alignment would be achieved when the scores would be equal, because then at least I can compare the loadings with one-to-one mapping, and that would be informative. At least I hope that will be informative. So, for example, in this case, it would be some kind of a rotation, and if I would even rotate it, they already seem to be more alike. So this would be a very easy way to do it, but of course this is not the complete solution, or they are still not equal. There's still a large difference in there. So my generic model for combining two data sets, and now we're getting to almost a PCA solution again, is actually, well, we got, in this case we have two data sets, and we compose them into three terms. So first of all, a low rank approximation capturing the common variation. Here I've got my common x1 and my common x2. A low rank for distinctive variation, and that's my distinctive x1 and distinctive x2. And of course I always have the error terms. That's always something I have to live with. Yeah. Sorry? They describe, in this case, this C is in terms of, let's say, if this is micro or mRNA, yeah? Then I've got, for example, 12,000 variables. So this C is of 12,000 variables. And this microRNA would be 1,000 or so. This would also be 1,000. So even though they are not the same, so but they describe some kind of common variation. That's the idea. But this is the generic approach. But now we're going to fill it in. So how would we solve for such a problem? And then this is where the PCA comes in to play again. So if I think about this difference and the separation of common and distinctive, then common and distinctive plus error terms add up to X. Well, it looks familiar like my PCA model. So I got my scores and my loadings and my error again. And if I write this out, if I expand this solution, if I have 5 principal components in my model, then I could use the first 2 components for my part, and my last 3 components, so 3 to 5, for my distinctive parts. And I already knew that they were distinctive and that they have no overlap because they are orthogonal, these solutions. So that's a nice feature. So in summary, so here actually I've got it, the TC, PC, DT, so my common scores, common loadings, distinctive scores, distinctive loadings, plus error model. So here I already solved one part of the problem. So this is my common, this is my distinctive, and different components explain different parts of the model. So this is really what I was looking for. Now I've got 2 data sets, so I do the same for exactly the one. This T should be there. This always goes wrong. So I do for the one data set, and for the second data set I also make such a model. But now what I'm trying to do, so if you look, well, so I've got these 2 formulas. What I'm trying to do is I'm trying to make these T1C and T2C, so my common parts, I want to have the same scores in this case. So my loadings are different, I know, because the one has much more variables than the other one. So that's not possible, so I will make my scores the same. So, and how to achieve this, and this is where for example, I'm going to pull the Disco SCA, actually, and first of all, this is the SCA part of it, where I'm trying to get common scores in this case. So, and actually what I do is I concatenate the two blocks. So I've got the same, the mode in this case of objects is the same. So I've got the same amount of objects, and I just put them alongside each other. So this is block 1, so my mRNA, this is microRNA. And then I get my scores and my combined loadings here. And actually, so this is a larger PCA version. So this is nothing really new. So I haven't found any common or distinctive scores yet. And but still, if I take only this part, I can get my x1 back, and if I take T times P2, I get my x2 back. So that's easy enough. This is the paper I'm referring to, which they've developed this, the Disco at least, which I will discuss here, because now of course I want to make them distinctive and common. And how do I do that? Well, therefore I use a rotation matrix, and actually that's exactly what I was talking about. It is a rotation somehow, so I want to rotate the one on top of the other. And if I look at this is my, so actually what I did here, this T and this P, I already split it up in 3 parts. I split it here. I reserved this part for my T1, T2, T3, and I can add them up like this, and then I would still end up with the same result. And then I would attribute this as a distinctive part times my distinctive loadings. But now what I try to do, what I want to do, is I force all of these components related to my second data set, I force it to 0. So they have no effect on my second data set. So they only affect my first data set. So I've got my first distinctive D1 times P D1, so I get my first distinctive part back. Only by selecting the appropriate rotation matrix here. Then here, for the second part, for my second distinctive data set, actually I force the loadings for data set 1 to be 0. Then I end up with distinctive scores for the second block, and I end up with this formula. So I already have half of my equations ready there. And then the third one, and this of course is the nice bit, because here I've got a common set of scores. That was what I was after, with a common set of loadings for the one data set and a common set of loadings for the other data set. And I have got these formulas. So if I look back, so here I've got all the elements of the formula that I've shown here. And so I actually separate so I've got now my common scores, and I wanna evaluate these two. I wanna compare these two, and I can do some analysis, combined analysis on these ones, and well look for commonalities in that, like which one correlate with each other and which one do not correlate with each other, and things like that. And well, here I've actually shown Disco, SCA, but actually there's also another method, Jive, which in formula is exactly the same. So it ends up with the same decomposition in scores and loadings. And O2PLS, for example, it's another one, but it has one additional change, is that common here and common 2, they don't exactly have to be the same. We try to be, they have to be as much similar as possible, but they do not necessarily have to be the same. And actually this has consequences, all these things, because solutions found can be more restrictive or less restrictive. So that would implicate the way you would interpret your data. And if, well, this of course is very nerdy, but it's orthogonality, and these are the constraints here. Actually, the Disco version has many constraints which are forced on the model. So the common part has to be orthogonal to the distinctive part, and my distinctive part for dataset 1 also has to be orthogonal to the distinctive part on dataset 2. So orthogonal, actually. So which is really, well, in a biological context, that's not really, well, not always the case. So that might prove that Disco is harder to yeah, actually it's perhaps more too restrictive to use in a biological context. Jive and O2 PLS, on the other hand, have more flexibilities. So and almost they are comparable, flexible. That's and consequently solutions might be easier to find if you use one of these models, but the results might be harder to interpret again, because you have more freedom to select your model, and it's easier to write model. So the interpretation of your results might prove more difficult. And the only way to do it actually is to experience this, is to do it, and you will do that tomorrow morning. So and I would suggest ask Patricia a lot of questions about it. And if, for example, now I look at the common scores of the data set that I used earlier, and in this case these are the glioblastoma data. Of course, I made the two plots, the common score plots of both data sets, and of course, like I said, they are the same. But that's what I forced to. So and luckily they are the same. You can see that the difference in explained variance is different, but that of course is logical because we're talking about the same scores but different loading, so they can have a bit different meaning. And if I look at my distinctive scores, so what is not common, so what is different, then I can see, and that's really informative, there's no systematic structure in the distinctive part. So there's no real clustering here of, actually what we see here is there is some, well, there's more obvious clustering in the different cancer types here than I had before I started this this procedure. And in the distinctive parts there is no real clustering visible anymore. So that would lead me to conclude that most of the interesting data is common and is shared between both, and there is no real further need to look into these parts. So I can focus only on the common bit. Similar to scaling in PCA terms, I also need to take care of scaling between the blocks if I have different data sets, if I want to fuse the data sets. So if I have loads of variables for, so like 12,000 variables here and well, let's say 1,000 variables here, then my variance here with more variables is much larger than the one with smaller variables. Consequently, if I would combine the blocks and do the analysis, the data fusion approach, my results will be influenced heavily by that, and my common variation in the block with the smaller variance will be lower, and that's what I find. So that's why you have to block scale, and actually what you do is you just adjust the variance of the whole block, the whole data set, and you set it to, for example, 1. So it has a variance of 1. So the total sums of squares, you normalize it to be 1. And you also do that for the other one, and then at least you know that one of these methods that it well, that is not biased towards one data set. So you can still compare. You can still compare the variables with each other. And how would you do that? Well, this is in here. I've selected 100 top loadings. Actually, it shouldn't be scores. It should be loadings. And actually, what I saw, what you see here, is that actually you see two groups. So actually on this diagonal axis here. So and I could relate these values to these to interpret them. So these microRNAs could be related to the other one, to the other mRNAs. And now I'm allowed to do that because yeah, I actually removed the rotational freedom that I had if I had the two PCA analysis separate. Then it still would be hard to compare these loadings to each other because, well, like you already saw, that the separation of time dimension was completely different in the one data set than in the other. So this one, so I'm now allowed to compare this one to each other and this one to each other. And another way to do that would be to order them and then, for example, focus on the ones here and the ones there and see if you can make some sense out of it. And this is the part where the expert knowledge is really necessary. So because here, I mean, statistics will stop, and I don't know if this will make any sense. I mean, this is where the knowledge of the researcher in question will come into play. So and then so yeah, so and of course you hope that this will be meaningful information, that you can really relate this to some kind of biological process and things like that. And or for that matter, you can also have a chemical process or anything like that, and you can see which parameters are of influence for that same chemical process. So to summarize or finalize, so what would be a next step? So, well, not only two, but more than two blocks. And for Disco, you can already do that, but it is kind of it gets more difficult to make a penalty matrix. So you can do that, but it's more difficult. Jive you can already use for more than two datasets, and O2PLS it's only two datasets, but they figured that and they extended it to ONPLS, which accommodates more than two datasets. And in here, actually, this is from the STATegra project. I actually used a couple of datasets, and I made the scores of the mRNA. I used that one. I plotted that one here, and in here I've combined microRNA, mRNA, methyl-seq, and DNAs together. So, and I hope that this would make some biological sense to look at these variables, underlying variables. So, and this is, I guess, this is where everything is heading for nowadays, to combine more and more data sets and hope that they make some biological or any sense at all, so that we can make a better interpretation of the data. So, and so concluding, so yeah, we can use the Disco O2PLS to select common variables, and even though I haven't shown Jive and O2PLS, I guess tomorrow you will do that in the exercises, so you can look. With common scores, the loadings, yeah, I mean, if you have these common scores, you can compare the common loadings. And actually, the thing is, you have to do that. I mean, because they're not separate anymore. So they are linked because you have made them common. So, and if you have identified what is in common, you can also separate what is not in common, so which is distinctive. So it's a kind of an interplay. Jive and O2PLS not shown here, but they are easier to extend to multi-block analysis, and the constraints of Disco might be proved too restrictive in some biological cases. These are the references, and these are the people I really would like to for their help here in this presentation, and of course you for your attention.